Now we're in section 2.3, getting information from the graph of a function. So we have a function here. We don't know what it is. We don't have it in function notation. We just have a picture of it. We have the graph of it. But from that graph, we can get a lot of stuff, a lot of information. So notice we have some questions here that ask us to use this graph to answer the questions. So we'll go down the list here. We have f of -1. So from the function notation we've talked about, this is, just a reminder that when you see something in function notation, that's f of x. So what this is saying is, it's basically telling us that x equals 1, and f of -1 means find the value of y when x is -1. So take a look at the graph and see if you can come up with the y value when x is -1. Hopefully you see that it is 0. It's this point right here. So we're just using the point. Then the next question is f of 0. So see if you can do the same thing. This is telling us now x is 0. What is the y value when x is 0? Take a look. Hopefully you can see that it is 2. Now the next one is one that students sometimes have trouble with, and it's basically asking us the opposite thing. So it's saying find the values of x. So we're looking for x values when f of x equals 4. Understand that that's the same as saying when y equals 4. So you're looking for any place on the graph where y equals 4 and then giving the x value of that point. So we can see if we think about it, you don't have to draw this, but here is y being 4. And we're just gonna think about, is there any place where we kind of intersect with that? And we can see that that happens up here and it happens over here. So think about what the x values are for that. And hopefully you can see that that's when x is a -2 and when x is 1. So those are the x values for which y equals 4. Now we're being asked, find the values of x, so again, x values, when f of x is greater than or equal to 0. If it's easier to see, there's no reason to not just change it to y being greater than or equal to 0. So it's telling us, essentially, whenever you have a y value that is 0 or positive, greater than 0, what are the x values for which we have that? So the way to think about this, I might change my color really quick here, is we can see that this is when y equals 0. And so we want to think about anytime an x value creates a y value that's greater than 0, we want to include that. So we're going to start all the way over here. So notice this gives us a positive y value. So when x is -2, we have a positive y value. And then I want you to kind of go across and see where that stops. Where does it stop? Where do we stop having a y value that is 0 or positive? Yeah, so hopefully you see that it is over here. So that's basically, notice from on that interval of x values, we end up with a positive y value or a y value that is 0. So that's how we answer this question. We simply give the interval for which this is true. So at -2, we have a positive y value. And all the way up until the x value of 2. So at the x value of 2, it looks like we have a y value of 0, but that's okay because we're being asked when y is greater than or equal to 0. So it can be equal to 0 as well. And then we have one more question. Find the net change from -1 to 1. So you might remember net change. We've talked about it. It's coming back so you don't forget it. The net change is found just by doing f of b minus f of a, in case you've forgotten. And remember that b is just the larger of the values and a is the smaller. So that is f of 1 minus f of -1. So go ahead, you can pause, find those two values. Again, you're using the graph. You don't have anything to plug it into. So use the graph, see if you can find the correct y values and then subtract them. All right, so we take a look. F of 1 is 4 and f of -1 is 0. So our net change is 4. really net change is just the change in the y values. You might notice it's just the difference between two y values. And as you can see, we have -1 is 0 and 1 is 4. So the net change there is 4. Now the function could go like this, but net change is called that because it is simply the change from the difference between two different y values, wherever they are. Okay, now we're going to talk about increasing and decreasing. This actually comes up in calculus as well, but we're just going to use our graph for right now to answer the question. So we have some definitions, and we're going to start with a function that is increasing. So the definition of increasing, and it's really what you think. So don't think, oh my gosh, how do I determine something's increasing? I know we have some definitions here that can be like, oh, what are they? But really all this is saying is a function is increasing if it's going up. If you're moving from left to right and the function is going up, it is increasing. That's what it is. But here's our formal definition. So f of x sub 1, so that's how I would read this thing here. I might say x sub 1, that's what I'm going to say. So f of x sub 1, you could also just think about that as y1, f of x sub 2, you could think about it as y2. And all that means is, if you think about this, it's saying that when you have an x1, your y1 is here. And what that definition means is that your y2 needs to be greater than your y1. So all it means is as you move along, your y needs to be higher. The second y needs to be higher. So y here, telling us that the function's increasing. Conversely, we have that the function could be decreasing. And that's simply the opposite, that your y1 needs to be greater than your y2. So if you have some point here, x1, y1, then the next point at x2 is going to have a y2 that is smaller than the y1. So it just means that the function's going down, that the y values are getting smaller as the x's are getting bigger. That's all. So now we have a graph. And notice that you're being given 3 questions. Where is f increasing, where is f decreasing, and where is f constant? And of course, this happens over the course of the function. So you are very welcome to, pause it, see if you can come up with the interval notation. What is the interval of x values for which the function is increasing, decreasing, or not changing at all? So you can pause, come back when you are ready. Okay, so where is the function increasing? So for example, we notice that we have an x value here. If I move along the function, say, here, just as an example, the function is going up, okay? The function is going up, meaning it's increasing because the y value at -2 is greater than the y value at -3. So that's by definition increasing. But we notice that right around here, it levels off. So right here, it stops going from increasing because it is like this, basically flat right at that spot. So our function starts increasing at -3. I'm not going to include -3 simply because it is not increasing or decreasing at -3 because it has just a point there. Nothing's happening on either side of it. Now that goes all the way up to that x value right here. So I'm just going to have to estimate that. It looks like it's a little bit more than -1.5. It's, although greater than -2. So what do I go with? -1.6 is what I have. So from there to there, we have increasing. Then it stops being increasing, and you notice it goes down. But then at some point it starts going back up again. So I'm going to use my union, and I'm going to say, hey, once I get over here, my function again stops doing one thing and starts doing another thing. So I'm going to say that it starts again at 1 to increase, and then it goes all the way up until, as you can see, 2, and then the function stops. So I can't go any further than that. So I have two intervals where the function is increasing, and then we can see there's this like middle portion where the function is going down. It's going down. So that is kind of easy because I should be able to see that it's just in between those two values that I already came up with that separates those two intervals. It's the interval in between. So from negative 1.6 to 1, I've got a function that is decreasing. Now, if the function were constant, it would just have a place where it's doing this, where it's just, it's that constant function that's just a horizontal line. Looking at this, I don't see anything. There's no place where it just continually gives us the same y value. Because of that, where is f constant? Nowhere. Nowhere at all. So we have a little bit more here with those kind of, definitions that are actually very straightforward, but just use, slightly more, what's the word I want? Slightly more, complicated language, I guess I would say, that we have to kind of work through. But we have this definition: a function has a local or relative maximum at a value. So this is an x value, c, if the y value at c is greater than or equal to all the other y values that are near that c value, that x value of c. So it's really just like if you have a point where all the other points are below it, so f of c, this y value here is the highest, everything else is underneath it, well then that's going to be called the maximum. And it's going to be, something like this. Conversely, you would have a local or relative minimum at an x value, c, if that y value that comes from that x value, c, is lower. So all the y values around it are higher. So that's what this means here. It's saying the other y values, the other ones, are greater than or equal to f of c, that y value. So it's going to be, here's your f of c, and then here's all your other y values around it. So they are greater, they are higher, and so because of that, they create this dip where f of c is at the bottom of that dip, and that means you have a minimum. So it kind of makes sense, what we know about maximums and minimums. So take a look. This is a graph that has some letters on it. So if you take a look, you can probably figure out which of those would be maximums and which would be minimums. And you can go ahead and pause it and write those on the blank spaces and then come right back. So we have our local maximums here. Again, what's really important to understand is that a maximum doesn't have to be the highest point on the graph. It just has to be that the other points around it, right nearby, are lower. So we can see that Q is definitely a local maximum because it's way up there, and everything around that top point is below that. But also S is also a maximum, and that is simply because the y values around it are lower than that. So that's what the definition says. For the local minimums, you can see that yes, P, R, and T are all local minimums. And that is simply because wherever that value is, right in the middle there, all the values, the y values around it, are higher. They are bigger. So by definition, that's all you need to have a local max or a local min. So make a note, be able to recognize those when you see them. So the last little bit here is solving equations and inequalities graphically. So we can use set or interval notation, but it kind of depends on what we're doing here. Now you might start, okay, I'm going to start solving this, but we're trying to do this graphically. Now the great thing about it is even though there's 3 questions here, it's actually really just one thing that we need to do, which is to graph each side of this. So what I mean by that is, if you take a moment and you graph y equals x squared minus 3, and you take a moment and you graph y equals 2x minus 3, that's how we can solve this. Because again, our job here is to solve this graphically. So if you're like, I want to do some other stuff, we've talked about other stuff. Yes, that was algebraically. Solving it graphically means taking a look at both sides, graphing both sides, and then trying to answer from there. So we're going to talk more about graphing functions, but if we think about any of these, we can really pretty quickly kind of come up with maybe some points, if that's how you want to do it. It's up to you. If you want to pause and see if you can graph both of these separately, then that would be you'd be in real good shape there. So I'll just put some values of x and y here to figure out what this looks like. If I put in -2, I will get 1, because -2 squared is 4, minus 3 is 1. I can put in -1. As you can see, that's going to give me -2. And if I put in 0, I'm going to get -3. So, did not make a very large table there. That's not great. But it's going to give me -2, 1, and -1, -2, and 0, -3. Now, something we talk about in the future, something that some of you may already know is this is a quadratic, so it's a parabola, and parabolas have symmetry. So we have actually talked about symmetry because we could plug in -x and get the same thing that we have there. This tells us that we're symmetric over the y-axis. So you know what? I'm just going to draw the symmetric points on the other side of the y-axis, and I'm going to know that that's what this looks like. So here's me doing my parabola. So I'm going to send it up. I'm going to send it up the best that I can. Do not judge me. Doing the best I can here. And then we also have this other function. So maybe I will put this in a completely different color because I think that will be easier to see. So I'm going to go Christmas colors for some reason. Y equals 2x minus 3. So I'll have x, y. Again, you can pick anything. You just have to, put the points on and then use kind of what you know about what these functions look like. So this is a line. This is taking a value, multiplying it by 2 and subtracting 3. So I will do, let's see, -1 is going to give me -5, and 0 will give me -3, and what else have I got? 1, sure, why not? -1, feel free to stop and see what this looks like here. So I'm going to give myself some points, as you can see, and then I'm going to put them on the graph. So -1, -5, so I'm just making it to the bottom of my graph. 0, -3, oh, okay, that's a huge point. 1, -1 is here, and then I have 2, 1. So here is my line. Okay. And extend that. And then now, just from that, we can answer the questions that we have. Believe it or not, we can. So the first question is simply, when do these two sides of this equation, when are they equal? And they are equal when, graphically speaking, their y values are the same. So you can see that they share a couple points. And you can see that the x values where they share a point is right here. So at 0, and up here at 2. So those are the two x values where this function, these two sides are equal, which again, if we look at them as functions, it's where they intersect. So you can see if you were to solve this algebraically, that part A, you would get 0 and 2. So you would be able to bring everything to one side, factor it, you'd get it. We're just looking at it graphically. Now the second question is x squared minus 3, when is it greater than? So understand that graphically speaking, this is just saying where is the parabola, when are the y values of the parabola greater than the y values of the line? So y values of the parabola being greater than the y values of the line. And we can look and we can see our answer. Notice that it's greater than, not equal to. So I'm going to be using some parentheses here, but it's also an interval. So we can see that our parabola goes up, up, up. I'm going to come from this side. So when our x values are negative, the parabola is going to go up, 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 up like this. The line is going down, 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 all the way until x being 0. So from negative infinity all the way to 0, we have the parabola being above, greater than the line. It is also true when it happens again at, you might be able to see the y value where the parabola is greater than the line. It starts again at 2. So notice at 2, the little piece of the line, and then the parabola is coming up like this, so the parabola is higher than the line. And they're just going to keep going. They're going to keep going. The parabola is going to go up, the line's going to go up, but the parabola is going faster. And so that goes out to infinity where it is greater. And then, kind of like what we saw before, is to answer this last question, it's actually really fast because we're asking, I mean, we do have equal to, so we have to think about the places where the two sides are equal, what x values make that happen. But it's really just anything that we didn't include already from part B. So we can see that there's this little point you're looking for when the green line is greater than the red parabola, and you can see that that occurs from 0 to 2. So in that little interval, you've got that the line is greater than the parabola, and that's what this piece right here is saying. It's saying when is the line greater or equal to the parabola. So equal to gives us the brackets, and then 0 to 2 is the interval over which that happens. And that's section 2.3.